Good evening, everyone. This is Celso Batalha, Evergreen Valley College. I hope this can reach you well after Martin Luther King Day, the day of service. And I hope you had a great time yesterday. And today we have an exam going on that's going to be closed at midnight. Then it's going to be open again on Thursday. For a second shot, not necessarily you will see the same questions. Today I didn't go over all the emails I received in the afternoon. I was at Evergreen. I had to proctor the exam in the morning, and again, if you are attending this chat room at a later time and you still are not aware of what's going on as far as midterm is concerned, the one that you don't go to the classroom with me, the one that you do online at home, you must have Google Chrome installed as a browser, and you have to enable Proctorio to proctor your exam. So basically your computer must have a camera, and once you start the exam using Proctorio, your camera is going to be on, and then you have to show your student ID, and then you have to show the page of notes that allow you to bring, and then you cannot leave the examination room, or it's going to flag as if you are trying to get information. Also, you're not allowed to go Wikipedia and Google around and try to get information elsewhere or having your book available. This is being taped. Alexis Cortez, you are there, and this is being taped now. If you have any specific question, you can ask after I deliver the content today. Unless it's a question regarding the class itself or the subject and the topics. Do you have any question regarding the subject of this week's subject?
I don't.
Okay, so then in about 1 hour or less than that, I will stop taping and then we can talk. All right?
Right.
Okay. So, what are we studying? We are studying stellar evolution, basically. First, let me make sure you can see my screen. And you should be able to see my screen now. And I am here. Oops, not that one. New York Times, not now. So last week we initiated star formation, and we closed with the steps that are taken for a star to be formed. And I think the main learning aspect of last week's class is that stars are formed out of a cold gas that exists in the galactic disk. And then if the density, or in other words, if the gravity is strong enough in certain regions to overcome the pressure that keeps the gas from collapsing, then gravity will bring the gas in, and eventually a star is formed. But as we also learn, these clumps that will give rise to stars are not motionless. They have motion. First of all, they go around the galactic center, and second of all, they also have their internal rotation. They have some quantity in physics that astronomers and physicists call angular momentum. So when gravity starts to bring that gas into the center of mass, then the angular velocity of this gas which means the angular speed of this gas, the speed in which this gas rotates around a center of mass, grows. Is the ballerina effect. Ballerina opens the arms and then has certain rotation. If she or he wants to speed up and spin up, it just brings the arms towards the center of mass of the body, which is close to the body. So by doing so, it speeds up, and the angular velocity increase, but the angular momentum is conserved. So you don't need to get so trapped in the physics aspects of it, but you need to know the rotation is initially in the clump itself. And as a result of this evolution, and is that when the gas falls towards the center of mass, the gas in fact falls towards a circumstellar disk that surrounds this prime sequence star or this protostar. And this disk itself is the one that rotates, and out of it, some of the disk that does not fall entirely into the star or onto the star, the remaining gas in the circumstellar material will provide enough initial material for the formation of planets, satellites, asteroids, comets, depending on the distance to the star. This is pretty much last week. Now, as the temperature and density in the core of the star grows, it reaches points where thermonuclear reactions will take place. And when thermonuclear reactions take place in the core, then as we know so far that the major ingredient in stars is hydrogen. So hydrogen in the core, not all over the star, but in the core, will slowly be converted into helium. And this process by which 4 atoms of hydrogen is converted into 1 atom of helium will provide energy to the star to keep the star from collapsing further. And then the star can shine out for most of its lifetime. So 80 to 90% of the stellar life is spent doing exactly this in the core, where most of its hydrogen is fused and converted into helium, plus energy and plus neutrino is then formed. Now, this week we start with, go to module, we start with, it's taking time here. This week we start with chapter 22, which is what happened when the fuel in the core, what happens when the hydrogen in the core is exhausted. See, where does the energy of a star come from? Well, it comes from fusing hydrogen into helium and producing energy. But what happens when the core itself is all filled with helium atoms, right? See, hydrogen, 75% of the content keeps being converted into helium. So eventually, all the hydrogen is used up, and the ashes of fusion reactions, which is pretty much helium atoms, is what will populate the core. So what happened when this situation occurred? So that is the main point of chapter 22. But before we go there, I would like to go over Hertzsprung-Russell diagram. I mean, Hertzsprung-Russell diagram is one of the major student learning outcomes of astronomy. You have to have a nice understanding of what this diagram is all about, and exactly what communication, what information this diagram can tell us about the star and its evolutionary stage. So if you go to the module in week January 8 to 13, Hertzsprung-Russell diagram explained. As long as you have Java installed in your computer. I don't know if I have Java updated in my computer. Let me just see it. Looks like so far so good. Whoa, it is. Okay, so here is, if you can see, is the HR diagram. The HR diagram is a diagram that relates luminosity and temperature. In a funny way, as you can see, usually in the horizontal axis of diagram, if you have studied mathematics or physics or introductory physical sciences, most of the diagrams in the horizontal axis show a growing number of values, whatever unities you have there in the x-axis. In this case, we have temperature, right? So you would expect in a normal diagram to have temperatures growing from the smallest value up to the highest value. And as you can see in this diagram, it's not the case. By the way, this is an important information that you might see in midterm number 3. So the temperature is scaling down. See, 40,000 all the way to 2,000. So the temperature diminishes in the horizontal axis. And in the vertical axis, the luminosity, which is the amount of energy the star itself puts out in space. Luminosity is not the same thing as brightness. As we saw last week, brightness is what you see when you go outside and then you look to the sky. When you look to the sky, you see stars of different brightness, and you do not know how far they are from you, because this distance is a factor that we need to figure out before we figure exactly what is the luminosity of the star, how much energy that star itself is putting out in space. Like a light bulb, let's say you have a light bulb that is 100 watts light bulb. It's pretty much close to you, is bright, and you can feel the heat. If you take that 100 watts, which is a measure of energy per time, if you take that 100 watts light bulb and you put on the top of a hill that I can see, not now, it's nighttime, but the hill that is in front of my house, I will see the brightness of that light bulb much less than it is when it's closer to me. And yet the luminosity is the same. The amount of energy that light bulb is sending out doesn't change, it's the same. But there is a factor distance that forces the brightness to be less than than usually is. Let me see one thing here quickly. See if somebody is asking questions. No, it's not. So far, so good. So again, luminosity is energy, and brightness is what you see of that source of energy, and that will depend, which means brightness will depend on how far or close you are to that source of energy. So the HR diagram is a diagram that relates this luminosity, this energy, with the temperature. So in the 1800s, beginning 1900, what astronomers did, once they had mastered the technique of spectroscopy and photometry, and they were able to pin down the stellar surface temperature with good precision, and also envision techniques to establish distance to the stars using parallax for once, or using stellar candles, like but not so much in the 1800s, but using other techniques to establish distances. In 1800, parallax was the major one. Then now we have a group of stars that we know the energy they are putting out, and we also know their surface temperature. So how, in average, hot they are. If you determine the temperature of the gas, take a scoop of gas in the stellar surface, and what temperature that is. what sort of energy that scoop of gas has intrinsically in it. So when astronomers did that, which means for the stars they had well-known information of distances and surface temperature and energy they were sending out, they organized this diagram, that's the HR diagram, Hertzsprung-Russell diagram, which was independently built by these two astronomers. They found that most of the stars, 99% of the stars or more, happen to be located in this HR diagram. And that's what you see in this red line over here. See that? So in the HR diagram, just to compare with the sun, here is in the window, in the left-hand side, you have the sun and you have a star, and the star is represented by this axis right here. See that? So 90% of the stars, they are located in this region here, indicated by the red line that astronomers call the main sequence. The main sequence. Okay. Now, there is another region in the HR diagram called the giants, and that is the region where they seem to be located. And there is another region called the supergiants, which are either blue supergiants or red supergiant. Why blue and red? Because of their surface temperature. See, the size of these stars are huge, are gigantic. You can see by the indication here, 100 solar radii, 1,000 solar radii for blue and red supergiants, right? And you have a minute group of stars called white dwarfs, and they happen to be located in this region here. So if you do a survey of HR diagram, and you bring images just to get an idea, this is what you got. So you have, let's pick one of them. Let's say this one here. So in the HR diagram, this is not, oh, that's better. You have most of the stars, 90% of those stars, they happen to be in the main sequence. See? And some of them, the remaining 10%, they are separated by the giant stars, the supergiant stars, and the white dwarf. Now, what does represent each one of these locales, each one of these stages? Main sequence, giant, supergiants, red or blue, and the white dwarfs. So that's the main point of this week class, if you will. So in this week, we are going to be studying what happened when the star exhausts its hydrogen in the core. When the stars are born, they are born out of with certain material, with certain mass. And if they are low mass, when they become a main sequence, when they are able to ignite these fusion reactions in their core, they are located in this region of the HR diagram. They are cold and they are subliminous. They are called M stars. Now, the sun, our sun is right here. The sun is a main sequence. It has an average temperature of 6,000 Kelvin and has a luminosity of 1 solar luminosity. Now, when you go to a star that is more massive, but is still in the main sequence, it is a star that is much hotter than it is the sun, but is also more luminous. So in the main sequence, in an HR diagram, you segregate the stars by their mass and luminosity. The less massive stars, they happen to occupy the lower right-hand side of the main sequence. And the stars that are still fusing hydrogen into helium in their core, but they are massive, they happen to be occupying the upper left-hand side end of the HR diagram. But the main point is eventually the entire hydrogen in the core is going to be used up to form helium. And then take note, these two things happen in the core. So think about the energy that is produced in the core, like the energy that is produced in the sun's core right now, is the one responsible for keeping the sun stable. The sun does not fall, does not collapse under its own weight. It's under its own gravity. But the gas pressure that is provided, that is fed up by the energy that comes out of the core, that gas pressure is not big enough to expand or explode the star. So the two forces balance out perfectly. So the sun does not expand under the actions of the energy produced in the core, and the sun does not collapse under the weight of its own material. So the sun is stable. Now, what happened when the energy that is responsible for providing this stability that comes from the core, what happened when that energy is gone? This is the point of this week class. And this diagram here might give some hints. And I tell you what happened. Please take note. I'm summarizing 2 or 3 sentences. Ready for? When the hydrogen is all converted in helium in the core contracts. Why is that? Well, the core contracts because the energy that was keeping the core stable is not there anymore. And the weight of the star that overlies the core is still on. The material is still there. And that weight, that material will force the core to contract, will bring the core into contraction. Now, as it happened with any gas, a gas that is contracted will heat up. The core heats up. It diminishes its volume and it heats up, first of all. As a result of that, in the region surrounding the core, fusion reactions are initiated, in which the hydrogen, not in the core, but in the region surrounding the core, in the shell surrounding the core, the temperature and pressure are just right enough to allow for fusion reactions to go on. And now we have a core that is getting hotter than it was previously because it's contracting, plus you have a shell of fusion reactions producing energy. The result of these two new effects in the region around and at the core sum up and adds up to provide more of a gas pressure in the layers inside the sun than the gravity force that brings the shells to the center, who try to bring the star to a collapse. In other words, when the hydrogen in the core is exhausted, the balance of forces are gone. The hydrostatic equilibrium, as we studied in last week, is gone. And as a result, the stars start expanding. And that's why this term giant star. So they are giants because they expanded. Now energy that comes out of the core and the regions surround the core overcomes the weight of the star, and the star tends to expand. And it becomes about 10 times as big as the star was originally. and that is called giant. Now, why red giant? As the outer layer, as the atmosphere, which is the most external region in the star, expands, as the atmosphere expands, the separation between molecules and atoms in the atmosphere increases. So less collision takes place, and with less collision, the temperature diminishes. And as the surface gets cooler, it gets hotter or redder. As we learned last week, the hotter the gas, the bluer it is. The cooler the gas, the redder it is. So red giant. So eventually these red giants, they undergo process which I will explain tomorrow. So tomorrow I will be focusing on this again. But what are the supergiants? Supergiants are stars that originally were in the upper left-hand side of the main sequence. They were massive stars that when they exhaust their hydrogen in the core, they become supergiants. See, they don't have a lot of a change in luminosity, but they have a tremendous change in surface temperature, and they are very luminous. They are red supergiants and blue supergiants. Betelgeuse is one of these such example. Antares is another example of this type of stars. And these little dudes over here, the white dwarfs, are low mass stars that eventually have completed their evolutionary cycle, and I will talk about them tomorrow. So let me stop now and see if whoever is there has any question about this subject here. I'm still taping. No question? Okay. Oh, that was a yawn. Okay, so I'm not putting you to sleep, am I? Oh, okay, so let me go. Sorry.
No.
Okay.
Sorry.
Okay.
I'm sick. I'm sorry.
No problem. No problem. No problem. Okay, so let me go now and go over the slides. This is an example of an evolving star. When the star completes their evolution, which means they go to the main sequence and they become a star like the sun, and they become what we call main sequence. When the hydrogen in the core is exhausted, we say the star is dying. And then what I was telling previously is the hydrogen is being converted in helium. But what I didn't say is that the fusion reactions doesn't stop in helium. It goes from helium and then carbon and nitrogen, oxygen, and neon, depending on which original mass the star has. It goes through a series of fusion in the core that creates new elements. And one of the processes in which the star might die is the one that is an explosive death, we call supernova, and in which several of the high mass type of elements we know are formed in a very short amount of time when the star is exploding. So stellar evolution is also the study of how atoms are formed in the universe. So when you look a lot around, ourselves, I'm here in a room, so there is metals that I can see, there is carbon because of papers and books. I have my body, so I have cells with carbon, iron, and all kind of things. All these atoms, with the exception of hydrogen and helium, all these atoms were formed in stars that no longer exist. And when our solar system came to be formed, it picked on this gas that had been populated with elements formed in stars that no longer exist. So as the universe age, as the universe evolve, so more of these atoms are formed. And then, so the universe is not always the same because stars are being born, stars are dying, and as a result of this cycle, new elements are formed, and the universe altogether becomes more metal rich as it ages. So, but when the stars die, they expel a lot of material back to the interstellar medium. So material that was used to form them is expelled back to the interstellar medium, but with some surplus, with some excess of metals the stars themselves created during their evolutionary phase. So this is a picture rendering what a star should be in its interior part. Have a stellar envelope, and we have a core with a hydrogen burning core. So it's a nice representation of what a main sequence star is. Okay? But look at this phase B. The phase B is when it happens when the star is not in the main sequence anymore, when the star is leaving the main sequence. So the core is completely now a helium core that has been shrunk by the weight of the star, but as you can see, there is a hydrogen burning shell still with the fusion reaction. So more energy as a result come out of the system. And this excess of energy will overcome the gravity itself at different layers, and the star expands. And can expand sufficiently depending on it can expand significantly depending on the initial mass of the star, which will govern the amount of energy itself that comes from the core. So Betelgeuse is this star over here, is one example of a red supergiant. Betelgeuse is invisible right now in the sky. If you happen to be attending or watching these at night, if you can locate Orion constellation, Betelgeuse is one of the brightest members in the constellation, if not the brightest, I seen with your unaided eye, and also let me see if I can show that in Stereo-9 software. There you go. So right now this is January 16. January 16. If you are in a nice location without too much light pollution, you can see a beautiful display of the sky. You have Sirius, Orion's belt. More above, you have Taurus, and the Pleiades, the star cluster. Okay. So Taurus, the ecliptic, where the zodiac is here represented. This is Castor and Pollux in Gemini. Have Taurus. Aries is, where is Aries? Is right there. That's Aries. The horns of the ram. And here's Betelgeuse. Even with this simulation, it can show how kind of a reddish it looks like, especially when compared with Rigel. Rigel is a star that is apparent magnitude is 0.15. As we studied last week, the magnitude of a star that has the least number is the brightest one, So Rigel is 0.15, Betelgeuse is 0.43. So Rigel is the brightest member in the Orion constellation, and Betelgeuse is the second brightest member. But Betelgeuse, when you look visually, just with your eyes, you look at these two stars, it's unmistakably that you can distinguish Betelgeuse and Rigel because of their color. Let me see if I can bring information, if I can. No. All right. Now, again, it is being shown here an HR diagram, and these lines here are theoretical lines, called theoretical tracks that show what happened with the star as they move in the HR diagram. Now, we use this word move in the HR diagram. It does not mean the star itself moves in space. Like the sun will evolve, the sun will become a red giant, but the sun is not going to move in space because of its evolution. But it changed its position as far as luminosity and surface temperature is concerned, and that impacts their position in the HR diagram. So a star like the sun, when the hydrogen is exhausted in the core, will move up and to the right in the HR diagram to the point that becomes a red giant. Red giant. There you go. Red giant. So a star like a massive star that is already a blue main sequence star, when it starts dying out and the core is now a helium core, the star moves in the HR diagram to the right only. Meaning this number here doesn't change, see? As the star is moving around, this number in this vertical axis doesn't change much. And this number represents the star overall luminosity during these phases. But its surface temperature changes dramatically, as you can see here. It goes from 26,000 and then can go all the way to 4,000. And as we learn, it keeps changing when new sequence of fusion reactions take place in the core of the star. Here are Omega Centauri is a globular cluster that indicates lots of white dwarfs, these bluish little dots in there. Let me see if that is the case. If yeah, the yellow, white in color, the main sequence stars similar to our sun. The bright stars are red giants. Oh no, they are not white dwarf. They are main sequence. Sorry about it. The blue stars have started helium fusion. Yeah, I have to read this again to interpret this. I will go back to you tomorrow on that. Jewel box is a cluster of stars, and and note the constant color between the bright yellow supergiant and the hot blue main sequence star. So the coloration is different. Those are main sequence stars, and this is an evolved star. Now, when you have a group of stars that are born together, they are of same age, but not necessarily of same mass. Right? So when you see the HR diagram like this of a young cluster, what you can tell about is these stars over here, since they all have the same age, but not the same mass, so we know the age is the same. And we know also that stars that are of less mass, they take longer to contract and to reach the point of fusion reaction in their core. We call that the zero-age main sequence. So when we look at this HR diagram of a cluster, it's about 3 million years, it's very young. So these stars, this dot here represents stars, low mass stars, that are still, slowly moving towards the main sequence. These stars over here already reached the main sequence, and this little dot up there is star leaving. Again, what controls stellar evolution? This is one of the discussions we are setting out probably next week or this week. I have to check. The stellar evolution is controlled by the mass of the star in such a way that low mass stars take longer to complete their passage towards the main sequence. And once they reach the main sequence, they stay there 80% of their lifetime or 90% of their lifetime. And when they die slowly, and they become planetary nebulae and white dwarfs. Whereas massive stars, high mass stars, more than 8 solar mass, they evolve quickly towards the main sequence. They stay short time in the main sequence, and yet 80% of their lifetime. And then they die in an explosive way we call supernova. So evolution goes fast for the high mass and evolution goes slow for the low mass star. Okay? Caitlin, I can see you there. Good evening. Now, this HR diagram is of a group of stars. You still have a bunch of them trying to move and migrate towards the main sequence. But you have a bunch of others already in the main sequence right there. So, see if we can get another one. Look at this one. This group, this star group, this open cluster, most of the stars are already in the main sequence. But you see, the high mass end is gone, is dead, is not there anymore. And the stars that are more massive than those of about 10,000 Kelvin, they are initiating their time of leaving the main sequence, the turn-off point. They are leaving the main sequence at that time. So astronomers that do theory about stellar evolution, they can create these theoretical tracks, and they can pin down how long it takes a star of any position in the main sequence, how long it takes that star in the main sequence to initiate their pause-main sequence phase, as we say, when they leave the main sequence. And if you have a group of stars formed at about the same time, and you do the HR diagram of this group, you can determine the age of that group by the star representative of the moment when the group itself leaves the main sequence. Right here, most of the stars that are main sequence are the low mass star. The turn-off point is right there. So it's a star of about, 5,000 and so Kelvin. And then you ask the theoretician how long it takes a star of a 5,000 Kelvin to evolve and start leaving the main sequence. And by doing so, you can address an age for that cluster. So HR diagram is kind of applications of HR diagram is important in chapter 22, and that's what we are initiating the talk today. Let me see if I can go back there. There you go. Go back once more. Right here. chapter 22. So that's pretty much for today. And tomorrow we're going to go with 23 and talk about the death of the stars. So what happened when they leave and they are off the main sequence. So I'm going to stop taping now, and then